Hi, class. In this recording, we're going to focus on the electrical activity or the action potentials associated with skeletal muscle fibers. This is a beefy topic, and if you haven't read your chapter yet on skeletal muscle physiology or muscle physiology, please take the time to read this chapter in your textbook. This is when things start to get particularly complicated. So let's dive in. As we look at muscle fibers, aka muscle cells, and the neurons are both electrically active. This means that we can have a change in voltage from one part of the membrane to another part of the membrane. When we think of electrical voltage, you can think of electric potential energy, or a difference in electric charge from point A to point B. Now, when our skeletal muscle cells or muscle fibers are at rest, there's a default voltage associated with them known as the resting membrane potential. And that default voltage is negative 90 millivolts. Negative 90 millivolts means that our skeletal muscle cells have a slight negative charge from the outside to the inside of the membrane, the sarcolemma. The slight negative charge is going to be maintained by an active transporter known as the sodium potassium pump that's constantly burning through ATP to move sodium and potassium ions against the concentration gradients. So, if we have an unstimulated or resting cell, the outside of that muscle cell is going to have a lot of sodium ions, and the inside is going to have a lot of potassium ions. As we look at those sodium ions that are on the outside of the muscle cell, that's going to give the muscle cell an overall positive charge on the outside and an overall negative charge on the inside. There are other proteins and other charges at play. There are large anionic proteins that are stuck on the inside of the membrane. So if we have a net negative charge on the inside of the membrane, or we have mostly negatively charged ions or anions on the inside of the membrane, we'll have that net negative charge on the inside. We're going to have excessive amounts of sodium ions on the outside, giving us an extracellular charge, or the charge to the extracellular fluid that is positive in nature. And it's worth emphasizing that our sodium potassium pump builds up a concentration gradient of potassium ions on the inside of the cell. So even though we have lots of positive potassium ions on the inside of the cell, what is not shown is all of the negative chlorides and the negative anionic proteins that are stuck in the cell, giving it a net negative resting potential on the intracellular side of the sarcolemma. So when the cell is at rest, we're going to have a net negative charge on the inside, and a net positive charge on the outside. If we stimulate or activate our muscle with an action potential, we're going to have sodium ion channels, sodium voltage gated channels open up, and sodium ions rush in. And as we add more and more positively charged sodium ions to the inside of the cell becomes positive. As we remove positive sodium ions from the outside of the cell becomes negative. And this negative charge, as the positive charge builds up on the inside of the cell, we refer to that as depolarization. As the inside of the cell becomes increasingly positive, we are depolarizing the plasma membrane at that physical point in the cell. After depolarization, we are going to have the sodium voltage gated channels close and the potassium voltage gated channels open. So now the sodium ions got stuck inside of the cell. The potassium ions, which have a concentration gradient that's high on the inside and low on the outside, will cause potassium ions to flow out of the cell with their concentration gradient when we open up the potassium gates, so the calcium voltage gated channels. The potassium rushes out. As we lose positive charges from the inside of the cell becomes more negative, and the outside of the cell becomes more positive. The decrease of charge on the inside is referred to as repolarization. So as we're working with our membrane, working with the skeletal muscle fiber, it's negative on the cell membrane has a negative charge at rest. And then we activate the muscle, sodium ions rush in, make the inside positive, and then potassium ions rush out and make the inside negative again. So we've just lost a lot of our sodium concentration gradient and our potassium concentration gradient. And in order to reestablish the initial concentration gradients of sodium and potassium, we're going to have a sodium potassium pump work to reestablish that resting membrane potential. And we'll remove the sodium and potassium ions back to where they originally were. Now, it's worth emphasizing this action potential is going to be self-perpetuating. It's going to travel down the length of the cell membrane so that we can have an electrical charge, or the movement of charged particles, go from one part of the muscle fiber across the entire surface area of the cell membrane and the surface area of those transverse T-tubules that transect or go across the inside of the muscle fiber. This wave of electrical activity goes across the muscle fiber is referred to as an impulse, a nervous system impulse, or action potential. Now, if we prevent the movement of these ions or the movement or release of the neurotransmitters, the acetylcholine, we can cause a muscle to be paralyzed. So different toxins are going to affect muscles in different ways. Primarily, we're going to target the synapse with toxins. And some pesticides are going to have a kind of enzyme known as cholinesterase inhibitors. And this protein, or this molecule, I should say, inhibits the enzyme cholinesterase. Cholinesterase is going to bind to acetylcholinesterase and cause acetylcholinesterase to not degrade the acetylcholine. What does this mean? This means that we're going to have way too many neurotransmitters in the synaptic cleft. We're going to have way too much acetylcholine, triggering way too many contractions of our skeletal muscle fibers. Pragmatically speaking, this means that we're going to continually contract and also fatigue all of our skeletal muscle fibers. This is a problem because our diaphragm is a skeletal muscle fiber. And if you only contract the diaphragm, that means you can only inhale and you have a really hard time exhaling. This can cause suffocation. Sometimes when we're looking at the spastic paralysis, this can be caused by a bacterium known as Clostridium tetani. Clostridium tetani releases a cholinesterase inhibitor that initiates the disease state known as tetanus. And when I say tetanus here, or lockjaw, I'm referring to the disease that causes our skeletal muscle fibers to all contract all at the same time. In particular, with tetanus, we're going to have the blockage of glycine in our spinal cord. And if we block glycine in our spinal cord, we are going to make it so that our motor neurons are going to function inappropriately. So we don't have the glycine in our spinal cord. That's going to cause overstimulation of our motor neurons and then spastic paralysis of our skeletal muscle fibers. Glycine, when it's present in our spinal cord, helps us to down-regulate the activity of motor neurons. So ultimately, having glycine in our spinal column or in our spinal cord prevents unwanted muscle contractions. Another kind of paralysis that we have is known as flaccid paralysis. So instead of paralysis associated with too many contractions, this is paralysis associated with no contractions. A common source of flaccid paralysis is curare. Curare is a molecule that will competitively compete with the acetylcholine receptor sites. And curare will bind to acetylcholine receptors, not trigger the action potential on the skeletal muscle fibers. So as we look at curare, it's typically isolated from plants. Traditionally, it's been used in poison darts or poison blowguns in South America. And when an animal is shot with a wooden dart that has curare on it, that animal in a short period of time will lose the ability to contract its skeletal muscle fibers and goes limp. Another form of flaccid paralysis isn't going to be caused by curare, instead it'll be caused by the botulism poison. Botulism is released by a bacterium known as Clostridium botulinum. Clostridium botulinum, if you do any kind of canning or food preservation at home, this is a bacterium that is capable of growing in an anaerobic environment. So if you don't do a good job of pressure cooking, particularly your ground or root vegetables, you're going to have a little bit of this bacteria slowly growing in your food products while they've been canned on the shelf. As Clostridium botulinum releases the botulism molecule, this molecule is going to prevent the release of acetylcholine from the axon terminal of the neuromuscular junction. High concentrations of this poison kill you. Low concentrations of this poison can cause localized relaxation of skeletal muscles. And we found that if we dilute this botulism toxin, we can inject it and cause people to have reduced wrinkles. Diluted botulism toxin is referred to as Botox. And typically it'll be injected around the eyes, around the eyebrows, to reduce the amount of wrinkles that we have visible on our face. That's all we have for this recording. As always, if you have any questions, please feel free to shoot me an email or post them on the class discussion board. And happy studies.